Hello, I'm Scene Jordan, and I will be presenting Physics 2211 Lab 3, Black Hole. This experiment is split into two parts. The first part is about determining the average mass of our black hole, while the second part is about finding the initial velocity of a spaceship flying towards the black hole from a planet and trying to leave the system without it crashing into any bodies, that being the black hole or the planet. Key concepts we will be using in the experiment is Newton's second law and how it relates to forces on an object, to its position and velocities, the law of gravitation from one object to another, and finally the idea of net force components when an object is moving in a nonlinear path. Here I have put the key concepts that is utilized in each segment of the experiment. In the first part, we will use the relation of momentum and force to derive the two components, the parallel and the perpendicular force components. Also, we'll use the force of gravity to find the mass of the black hole, which is done by rearranging the equation to get the magnitude of the mass in particular. In part 2, we will use the law of gravitation to find all the forces being placed on each system, that being the planet and the spaceship. And after finding all these forces, we will use Newton's second law to update the velocity and position of the spaceship as it's moving through space. The objective of this experiment is to find the mass of the black hole and calculate the initial velocity of the ship to overcome the gravitational force probed by the black hole so the spaceship can leave the orbit of this entire system. We can expect that as we move closer towards the black hole, the ship's momentum will change due to the influence of the gravity. For part 1, our system will be the planet and their surroundings will be the black hole. For part 2, the system will be our spaceship and the surroundings will be the planet and the black hole. And for both parts, we are assuming that we are in space and there's no other external forces. Here are the conditions for part 1's computational model. The initial conditions consist of the universal gravitational force, the mass of the star, and the change in time interval. Next, the iteration conditions use the same idea explained prior, but in the coded context. We first determine the momentum of the star and force and use that to find the components for the parallel and perpendicular components. Using this net force, we can finally rearrange the gravitational force equation to solve for the mass of the black hole. The results of part 1 can be seen here, where the magnitude of the net force at the final position is about 8.69 times 10 to the 28 newtons. The magnitude of the parallel force is 2.54 times 10 to the 28 newtons, and the magnitude of the perpendicular force is about 8.32 times 10 to the 28 newtons. From these conditions, the average mass found is roughly 1.16 times 10 to the 34 kilograms. We see that the star follows a slightly elliptical path around the black hole due to the black hole's gravity. As the star got closer, the momentum increased for the star and rapidly swings around the black hole, showing an increase in the component's magnitude as a result. Some possible errors are solely based on the initial conditions, where rounding errors could slightly skew away from the real-life conditions. For part 2, we use the mass of the black hole found in part 1, as well as the other conditions, such as gravity constant, mass of the planet, mass of the ship, and the change in time. The max time can be changed to show the path of the ship. The iteration steps revolve around finding the gravitational force on the ship based on the surroundings and adding those forces up to update the velocity and position of the ship. After trial and error, a possible initial velocity of the spaceship to leave the system is about -7 times 10 to the 7, 3 times 10 to the 6, 0 meters per second in vector form. The shortest distance that the ship came towards the black hole is about 3.99 times 10 to the 9 meters. Shown prior, the ship comes close to the black hole and then leaves the system with the found initial velocity. This is due to the fact that the initial velocity was enough to overcome the gravitational force from the black hole. Possible errors from this is solely from the initial conditions as well, just the same way as part 1, as these could also skew away from real-life conditions. How does the net force component differ from the rate of change of momentum and its components? Well, in general terms, these components are equivalent to one another, as we are using them interchangeably. As you can see, the net force components are equivalent to the change of momentum over time, all equating to the overall net force. In terms of expression, however, the dp dt is usually meant to denote an instantaneous change. What initial velocity would the spaceship need to orbit the black hole? Well, there are many answers to this question. And from my trial and error, I found that -1 times 10 to the 5, 1 times 10 to the 7, 0 meters per second in vector form cause an orbit of the black hole. And to achieve a more circular orbit, you can decrease the x and y speeds until the circular path is achieved. That is my presentation. Thank you for listening.